Every curve is secretly two curves. There is its height, where it is right now, and there is its steepness, where it is heading. Differentiation is the machine that reveals the hidden second one. Feed it a curve, and it hands you back the curve of that curve's own slope. Let's build the machine, then let it loose. How steep is a curve at a single point? That's a tricky question because slope needs 2 points, not one. So we start with an approximation. Pick a point on x cubed, then a second point a small distance h away, and draw the line joining them. It's close, but not exact. The real insight is watching what it becomes as h shrinks. The slope of that line is the rise over the run. Written out, it's the quotient shown here. Expanding the cube and canceling the h in the denominator leaves 3a squared plus 3ah plus h squared. Now let h go to 0. The second point slides into the first, the line stops being a guess and kisses the curve, and those two h terms simply vanish. What's left is 3a squared, the exact slope, at any point a. That number is the slope at one point. But nothing tied us to a single point. The very same limit works everywhere, and it hands us a formula. The derivative of x cubed is 3x squared. Here's the part most explanations skip. Don't stop at one point. Sweep the tangent along the whole curve and record its slope as a new height. Those heights trace out an entirely new curve, a parabola. The machine just turned x cubed into 3x squared. And a warning it plans for later. At the origin, the slope is 0. The tangent lies perfectly flat, but the curve does not turn around, it keeps climbing straight through. So a flat slope does not always mean a peak or a valley. Hold that thought. Now, let's learn to read curves fluently. 3 tiers, stacked. The curve itself on top, its slope in the middle, and the slope of that slope on the bottom. A scan line will walk across all 3 at once, so we can watch them react together. The top curve has a hill, then a valley. 2 places where it turns. Now, watch the middle tier. Every time the top curve turns, its slope curve crosses 0. 2 turns, 2 crossings. And the bottom tier, the slope of the slope, crosses 0 just once, exactly where the top curve stops curving downward and starts curving upward. That single crossing is the inflection point. So the turning points of a curve are hiding in plain sight, 1 tier down, marked by a 0. That's the whole grammar. Now, let's use it on curves worth meeting. Feed in a sine wave. Its slope is a cosine wave. The very same wave, only slid to the left by a quarter turn. Differentiation didn't reshape it, it marched it forward. Differentiate once more, and it slides again, landing on negative sign. Each derivative is the same wave, nudged another quarter turn to the left. The grammar from before still holds perfectly. Walk the scan line to the crest of the top wave, where sine stops rising. Directly below it, the cosine is slicing through 0. The peak of the curve sits exactly above the 0 of its slope every single time. But sine hides one more secret. Look at the top tier and the bottom tier together. They're mirror images, one flipped upside down. The slope of the slope is the negative of where we started. A curve whose bending always points back toward home. That one equation is why a plucked string sings, why a pendulum swings, why almost everything in nature that repeats. Some curves fight the machine. This one just surrenders. Feed in e to the x, and its slope comes back. E to the x, the exact same curve. Differentiate again. Same curve, a third time. 3 identical tiers. The one shape in all of mathematics that is its own slope, forever. Sweep the scan line across, and the 3 dots never break rank. At every value of x, the curve, its slope, and the slope of its slope all read the same height. Nothing to solve here. Just a curve perfectly in step with itself. Now the bell curve. The shape of averages of measurement error, of very nearly everything the world throws at us at random. Its slope rises on the way up, then falls on the way down, so the middle tier is a single peak and valley. Familiar so far, but the real prize is the bottom tier. Watch the slope of the slope as the scan line crosses. It cuts through 0 at exactly -1, and again at +1. Two crossings, and they are not arbitrary. They mark the 2 points where the bell stops curving downward and flares outward. This is called the shoulders of the curve. Draw those 2 crossings straight up to the top curve. They land on the bell's shoulders, the precise spots where its bend reverses. And on the normal distribution, those points already have a name you know. The standard deviation, left and right. The bending of the curve is where the statistics live. One last curve, and the hardest of them all. A wave trapped inside a shrinking envelope. A plucked guitar string fading to silence. A car's suspension settling after a bump. A bridge steadying after a gust of wind. Decay and oscillation, tangled together into one shape. Differentiate once, then twice. Both derivatives oscillate too, each caught inside its own fading envelope. It looks like chaos. Surely, here, the tidy rule from before finally falls apart. It doesn't. Watch each crest of the top wave, every point where it momentarily stops rising. Directly beneath it, its slope is passing through zero. The very same grammar as the plain cubic we started with, only now it's buried inside a fading tremor. Peak after shrinking peak, the rule never changes. Straight lines or shrinking tremors, it makes no difference. The story of every curve, where it climbs, turns, or bends, is written one tier down, wherever its derivative crosses zero. Learn to find that place, and we can read any curve ever drawn, which is exactly the skill we'll need next. 5 curves, 1 lesson. A cubic, a wave, the untouchable exponential, the bell, and a fading tremor. Read any of them, and the whole story sits at a single place, where its slope falls to zero. Every curve, and the hidden curve of its slope, with one machine standing between them. Coming up next, we put that machine to work, using derivatives to find the very best that anything can be.